Hi, welcome back to Physics Teacher, the channel that prepares you for the Waterloo Math and Science contests. In this question, we need to prove that for all integers a and b, there's going to be at least one pair of integers kl for which this is true. Give it a try, and I'll be right back with the solution. Alright, so what we need to do first is try to look at some patterns. So we're going to take some values for a and b, and we're going to sub it into this equation to see what we get and see for what values of k and l that might work, to see if we can find some patterns first. So let's do that. Alright, so if a is 2 and b is 1, we can substitute those values into this expression to get 3. So what values of k and l in this expression will also give you 3? Well, it's pretty easy to see. This is 3. If that was 3 times 1 and k was 0, that would work. So if k was 0 and l was 1, that would work. Well, what if a is 4 and b is 1? Well, substituting that in here, we have 4 squared, which is 16, plus 1, which is 17, minus 4, we get 13. Okay, so we can see if L is 2, 2 squared is 4, times 3 is 12. If we had one more, that would give us 13. So that would be K is 1 and L as 2. So here we have a pattern. Notice that I made A even integers. And if A is even, that means A divided by 2 is also even. And so we can look at k as being a divided by 2 minus b. So if we did that in this case, we'd have 2 divided by 2 is 1, minus 1 is 0. So that works. Alright, what about in this case? 4 divided by 2 is 2, minus 1 is 1. So that works. Well, what about L? What's our pattern for L? It looks like L is just, well, half of A. Right? It's just A divided by 2. So that works for both cases. But will this work for every case where A is even? So let's try substituting that into this equation for K squared plus 3L squared. So if K is A divided by 2 minus B, that would be all squared, plus 3 times L, which is A over 2 squared. So let's expand this, and we will get A squared, all divided by 4, minus 2AB, all divided by 2, so those 2's will cancel, and then plus B squared, and then we have plus 3, and this is A squared over 4. Well, here we have A squared over 4, plus 3a squared over 4 just gives us 4a squared over 4, where our 4's will cancel. And then we have minus ab plus b squared. So rearranging, we get a squared plus b squared minus ab, which is exactly what this is. So yes, this will work for every case where a is even. But what if a is not even? Let's try some other examples. If we had a as an odd number like 1, and let's make b even. So if we substitute these values into this equation, we get 3. Okay, well that'll work if k is 0 and l is 1. Well, what if I substitute a as 3? Keep it as an odd number, but I'll keep b as an even one. That gives us 7. And so what we could do is, if l is 1, we could make k 2, and that would give us 2 squared, which is 4, plus 3, which is 7. So this case looks similar to the previous case, except what we have here is b as being even, and therefore b divided by 2 would be even. And so if k is b divided by 2 minus a, and L is b over 2, right, which works. It's very similar to our last example we can show that this is true with the same algebraic expansion for all k squared plus 3l squared. So we've shown that this is true for any case where a is even and for any case where b is even. What about if they're both odd? So let's try some examples there. Let's say a and b are both 1. If we plug that into this equation, we get 1 plus 1 minus 1 is just 1. Alright, well, what values for k and l would work? Well, if k is 1 and l is 0, that would certainly work. Alright, so we need some more examples here. So let's try a as 3 and b as 1. That'll give us a value of 7. And so if k is 2 and l is 1, that works. Now, if in this case, if a and b are both odd, what we have is that a plus b and a minus b would then be both even. And so if I look at the case where k is a plus b divided by 2, right, that would be an even number divided by 2. That also gives us an even number. And if L is a minus b divided by 2, that works as well. So you can see in these two cases it works, right? If we have 1 and 1 for a and b, we have 1 plus 1, which is 2, divided by 2 is 1. And 1 minus 1 divided by 2 is 0. And you can show it works for this example. All right, well, we need to show it works for all possible examples. So let's substitute these in for k squared plus 3l squared. So what we're going to get is a plus b divided by 2 squared plus 3 times a minus b divided by 2 squared. And let's see what this is going to be when we expand it. So when we expand it, we'll have a squared plus 2ab plus b squared, all divided by 4, plus 3 times a squared minus 2ab plus b squared, all divided by 4. And we can collect like terms here. So here we have a squared and 3a squared divided by 4. So that's a total of 4a squared. And we'll make the whole denominator 4. Here we have 2ab plus negative 6ab. So that gives us minus 4ab. And then we have b squared plus 3b squared is plus 4b squared. So all the 4's are going to cancel, and we're left with a squared plus b squared minus ab. So this shows that if a and b are both odd numbers, there is values for k and l, which will make this equation true. And if either a or b are even, we showed previously that there are values for those that will make this equation true as well.